Assalamualaikum, I Bintu Madam. Today, my group and I will present Experiment 6 about High Performance Liquid Chromatography, short form as HPLC. Before we start, allow me to introduce the group members, which are Dayang Zulaika, Bibi Kashrina, Farah Ain Najwa, and me myself, Putri Idina.
Now, I'm going to introduce to you what HPLC is and the two different detectors involved in the equipment. HPLC is an analytical technique used to separate, identify, and quantify components in a liquid mixture. It involves passing a liquid sample through a column with a stationary phase, causing components to separate based on their interactions with the stationary phase. There are two different detectors in HPLC: the refractive index detector (RID) and diode array detector (DAD).
RID is a powerful analytical technique used for the separation, identification, and quantification of compounds in a mixture. Universal detection compound without chromophores, non-destructive nature allowing for further analysis of the elution fractions, and suitable for analyzing compounds that might not be detected by other methods, such as UV detection, are advantages of RID.
I will be focused on the diode array detector or DAD. DAD is a type of detector in HPLC that uses an array of diodes to measure the absorbance of light across a range of wavelengths simultaneously. This allows for increased sensitivity, flexibility, and the capability to provide a full UVB spectrum for each peak in the chromatogram. The technology enables detailed characterization of analytes in complex mixtures and facilitates accurate quantification by comparing absorbance values at specific wavelengths. Using a diode array detector in HPLC involves several sequential steps. After preparing the sample and selecting an appropriate HPLC column, the instrument, including the DAD model, is set up and calibrated. The user then determines the wavelength range for detection based on the expected absorbance characteristic of the analytes. Upon ejecting the sample into the HPLC system, the DAD detects the absorbance of eluting compounds at multiple wavelengths simultaneously, generating a complete UV spectrum for each peak. The collected data is then analyzed to identify and quantify components in the sample, taking advantage of the detailed spectral information provided by the DAD. Results are interpreted and the final report includes concentration of each identified component.
Next, there are several steps in HPLC that is needed to be done. The preparation of the sample, ensure that your sample is properly prepared, and then set up the HPLC instrument by checking and adjusting parameters such as flow rate, column temperature, and detector settings. You also need to prepare the mobile phase, which is the liquid that carries the sample through the column. Inject the prepared sample into the HPLC system. The separated components are detected by a suitable detector like DAD, which is diode array detector, and RID, which is refractive index detector. Both diode array detector and refractive index detector are valuable detectors in HPLC. DAD is more versatile in terms of compound identification due to its spectral capabilities, while RID is often preferred for its universal detection capabilities, especially when dealing with compounds that do not have a strong UV absorbance. And last but not least, for data analysis, we can identify the components in the sample from the chromatogram. We will explain more details on HPLC in the next part of the video. This is the mobile phase in HPLC for refractive index detector. The refractive index detector measures changes in the refractive index of the mobile phase caused by the presence of analytes. Some common mobile phase used in RID are acetonitril, methanol, and isopropanol. In this HPLC, a guard column and analytical column are two components often used together to enhance the performance. The guard column is a short column placed before the analytical column. It helps maintain the integrity of the analytical column, ensuring consistent and reliable separations over time. The analytical column is the primary column, where the actual separation of sample component occurs. The analytical column contains the stationary phase, which interacts with the sample components as they pass through the column.
The stationary phase is the immobile part of the chromatographic system, and it interacts with the mobile phase and sample components to facilitate separation. The choice of stationary phase depends on the nature of the analytes and the separation goals. Common types of stationary phase used in HPLC with RID are normal phase, reverse phase, ion exchange, size exclusion, or gel filtration. The choice of stationary phase influences the selectivity and efficiency of the separation process. In HPLC with RID, the refractive index detector is particularly useful for compounds that may not have strong UV absorbance, as it detects changes in refractive index caused by sample elution. When working with RID, it's important to optimize the chromatographic condition, including the choice of stationary phase, to achieve the best separation and sensitivity for the targeted analytes in the sample. When using HPLC with RID, sample usually be put in a vial that was made from glass. In the sample holder, each sample has their own numbers. This is to indicate the position of the samples in the sample holder. We can choose which sample that we want from the monitor according to the numbers of the sample holder. Apart from that, we can also control the amount of sample that we need and adjust the temperature from the monitor. In addition, in a degasser in HPLC with RID is used to remove dissolved gases from the mobile phase. This helps maintain stable and reliable baseline signal in the RID, improving the detector sensitivity and accuracy in detecting compounds in the chromatographic analysis. The removal of gases prevents fluctuation in the refractive index baseline, ensuring precise and consistent measurements of sample concentration during the separation process. That's all from us. Thank you.
Let's discuss further about our experiment. We can find the retention time and the peak area of caffeine from the results. From here, it is possible to determine the amount of caffeine in a soft drink sample using the response factor method. The concentration of caffeine present in a sample of the soft drink can be determined using the following formula. By using the obtained response factor, which is 113,100 mg/ml, we were able to find the concentration of caffeine in each sample, which are 42 ppm, 1.3887 ppm, and 1.1314 ppm respectively. Throughout the whole experiment, we need to take precaution steps to avoid errors. First of all, do not inject the solution into the chromatograph until you have shaken it thoroughly for at least 5 minutes. The solution must be fully dissolved to achieve accurate and reliable results. Besides that, rinse and clean the syringe before and after each sample is injected to prevent any contaminants and other solutions that might jeopardize its efficacy. To avoid clogging in the column, check for protein precipitation, which may happen when stabilizing agents are removed during fractionation. Lastly, avoid the formation of bubbles during the experiment because when the measurement is taken, any disturbance in the column could have an impact on the reading. To conclude this experiment, we achieved all our objectives in the experiment with great success, as we were able to obtain the retention time of a standard solution, caffeine peak in a soft drink sample, and the amount of caffeine in soft drink sample using the response factor method.